we're done with this presentation, object lifecycle for now, because we discussed destructors, constructors, copy constructors, which play a very important role. So this time we're switching to our next topic, and I posted it, and it will be related to our next upcoming homework, which is saying dynamic stack of integers using linked list. We're going to discuss linked data structures. And we're going to discuss the possibility of having objects in memory which are pointing to one another. So, for example, a linked list consists of a sequence of objects known as nodes. It's just by definition. So these are objects. The object typically, so this is like a little demonstration of a linked list. So supposedly we have some objects which are represented by these rectangles. And so when you see the numbers here, 12, 99, 37, it's like showing that those objects actually contain some payload. They could be used to contain some values, or maybe pointing to other objects, or containing something else. So they can be made useful. They could do something useful. In this presentation, we sort of like will stuck with just storing integers in them. All right. So, but the idea is this: one object of this type node could be pointing to another node. This node could also have pointer to another node. And eventually this pointer could be set to null, indicating the tail of our list. Basically saying, okay, you have the beginning of it, but at some point the list has the ending. So we have a sequence. And it can also be traversed. If you have access to the beginning of the list, then you can go to the next one, and at some point say, okay, there is no next one. So I'm actually I was able to traverse the entire sequence. So each node in this discussion will contain basically some data fields or useful payload, but also a link pointing to another node, which is of course a pointer to another node. Optionally, you can have also link pointing backwards. That would be called double linked list. So a very simple structure, remember struct is a class which has everything public in it, could have this integer data, this is our payload, and also pointer to another node. This is sort of like a curious syntax. Is when I first saw it, when I was actually learning C, I first saw something like this when I was learning C way back. And I just thought, wait a minute, that's kind of interesting. We're in the process of defining what node is. And yet already we are using a pointer to the node. It's sort of like contradictory, but the standard, both C and C++ standard, allows this to happen. You can use indirect references to instances of this very structure or class. It's permitted. It's okay to use pointers, which would allow us to construct something like this inside our class. All right. However, if this was not a pointer, but node used directly without any kind of indirection, then this would be a syntax error. C++ compiler wouldn't like that at all. It would say, listen, this data type is being defined, but you're already using it. However, doing it with pointers is allowed. Well, perhaps to answer the question, why is it allowed, is that what happens is that we have an object. And when it's constructed, this object, like, I like to draw them like 3D shapes, showing that this is an actual object in memory. And it can have a lot of things inside. Integers and pointers and other objects. It could have a lot of things inside. So, but if you look at pointers, they're all the same uniform size. And basically, it's okay to have a little pointer that will be later pointing at runtime to this object. And so if I have a copy of it, let me try this. Control C, make a copy of it. So if I have a second object like this, it's okay to have a pointer that points to another type, just like this one, another instance in memory. So this is allowed because pointer is not an object. It's just another integer-like thing that contains an address of this object. So this is allowed. So this is not a problem, right? So just to show you that having a pointer to node where we're still defining what node is. We're still in progress of defining it. This is where the definition is ending. But using a pointer to it is already okay. All right. So obviously, we need to allow this to grow dynamically and shrink. So the size of the list can vary. The list can grow and it could shrink. And the program can control how the list is built and managed and traversed and all that. So since those things can be created dynamically or can be linked during the program execution, what we end up having here is that if we create more of these, more copies of these, let me actually erase this temporarily to make it cleaner. And if I make more copies, so I've created some objects. I could have created some of these nodes with some payload, but then later on I may be able to do something like this. Okay, have this one pointing to here, have this one pointing to over here, and have this one pointing to yet another one, and finally this one points to, has a null pointer saying that, okay, this is the end of the list. Basically, a physical location of these nodes is not necessarily the logical sequence, right? So they can be located in memory, you know, address 1, 2, 3, and 4, but they can be linked in a different order. So the physical location of them does not necessarily reflect the actual logical arrangement or logical sequence, because it's up to the program to how to link those things. But 37 could be created first, and then 12 could be created, and then 99, but then we decided to link them in a certain way. And so the logical order does not reflect the actual physical order of these objects in memory. This is a logical order. Now, another part of this discussion is, how do we design something like this? What could be potential ways to maintain lists in our programs? What are the options? What could be design approach to implement something like this? One solution, there are actually three solutions, three classically recognized solutions to this.